Okay, so now we're going to be discussing about common Laplace transforms. Now, as previously discussed, there are four most common ones. We have polynomials, we have exponentials, provided that s is greater than a, we have sine, and cosine. Now, these aren't the only ones, and in order to apply to find the Laplace transform of it, first, for this one, we have to use induction. What that just means is test cases 1, 2, 3, and then generalize it to k and k plus 1. I will spare you the details, and I'll just give you the result in the end. This one we can apply direct integral. This one, or rather these two, there's two ways for us to go about it. We can do integration by parts, which is rather tedious and mathematical, or we can use the following properties. Sine of bt is just e to the j bt minus e to the negative jbt divided by 2, j. Cosine of bt being equal to e to the jbt plus e to the negative jbt divided by 2. And from here, we're able to directly show that these two we can just apply the direct integral definition with. Now, are these the only ones that we care about? Not really. There are actually a lot more. 5, we have step function. So the step function looks like this. Nothing at time t less than 0, but once it hits t equals 0 or greater, is just a continuous rectangle. Now, this, because it's kind of like a constant, is of exponential order and therefore has a valid Laplace transform. So that's okay. What others? Well, there's also delta function, given by delta of t. Now, the conception behind the delta function is that it is something that has infinite height, but unity area, because it's like a distribution. So you suppose that this rectangle represents your distribution with an area of 1. But we can also say that this could represent our area of 1, this could represent our area of 1, so on and so forth. And before we know it, we can approximately represent this as an arrow that shows the delta function's magnitude centered at 0. In this case, 0. If we were to shift it, it would be centered around, instead, t naught, for example. So these are the 6 common Laplace transforms, and actually combination cases of them are also valid. These are actually properties. Now, just for these 6, I will write the results. 1. T to the n has a Laplace transform pair, which we use the bidirectional arrow, of n squared divided by s to the n plus 1. Now, the idea is then, when whichever power we have, write a factorial on top, divided by s to one more power. E to the at, we have the Laplace transform 1 divided by s minus a, provided that s is greater than a. This condition is mainly because, as discussed previously, if we didn't have this condition upheld, then the integral would diverge. Therefore, we can't find a valid Laplace transform for it. 3. Sine of bt. The Laplace transform of this is b divided by s squared plus b squared. Or subsequently, we have the constant on top divided by some squared parameters. This is important because if we have cosine of bt, we have the same bottom part, except there's an s on top. Now, for the viewer, I challenge the viewer to prove that these Laplace transforms are true using the definition, to kind of get a feel for why the results are as they are. And then later on, we can just generally apply the different properties, which will be discussed in the next video. Now, 5, u of t is not necessarily very interesting. This actually just becomes 1 over s. But u of t minus t naught, though, is interesting, because this is the idea of the time shifting property. So we have some kind of exponential negative t naught s divided over s. That is the exponential, or that's the time shift rule. 6. The delta function, because we are asking the Laplace of the delta function, we're asking for the area underneath the curve. And for a delta function, its area is 1. So the bidirectional arrows shows that for a delta function, we have 1. However, if we were to apply a time shift, and once again, I challenge the viewer to show why this is the case, this becomes e to the t naught s. So that is the result that we end up getting from applying the delta function, or the delta function with some time shift in it. So these are the 6 common Laplace transforms. Now, for the viewer, just in preparation for the next video, I want the viewer to try out these few problems. All of these you can definitely just apply the transformation of, and you are able to show that there is a valid Laplace transform for all of these. Until next time, thank you.